As it says on the slide there, I'm from University College London, and I was very pleased to see that 3 of the 4 presentations so far this morning referred to UCL, either explicitly or implicitly, and this makes 4 out of 5. But in fact, I'm wearing a hat today really on behalf of ICSU, the International Council for Science, is the main orientation of this talk in the next half an hour. Before I get going, I'd very much like to thank Elsevier and particularly Dr. Gali Halevi for inviting me to come here today and participate in this very stimulating activity. Well, first of all, ICSU, International Council for Science, that's the top-level international body for science. It has 121 national scientific bodies representing 140 countries. So in the case of Australia, it's the Australian Academy of Science, in the US, National Academy of Science, and in the UK, Royal Society, and so on. And then it also has 31 international scientific unions, so those for astronomy, crystallography, geodesy, geophysics, etc., are all the participants in ICSU. So when things are discussed in ICSU, they're discussed essentially at the top level internationally of scientific activity. And the stuff I'm going to talk about today has largely been agreed unanimously by ICSU, even at that kind of level. And ICSU's strategy has a very useful vision. I'm sorry this slide is just words, but it has a useful vision because it says that ICSU sees a world where science is used for the benefit of all, excellence in science is valued, and scientific knowledge is effectively linked to policy making. So 3 components there. But then as far as data is concerned, which is the focus of these 2 days, in such a world, universal and equitable access to high-quality scientific data and information is a reality. So in a sense, what I'm going to talk about now, and what this whole meeting is about, is how to make the reality of access to information and the complexity that we've heard about so far. So what I want to do as an agenda for my talk is to present the ICSU journey, a series of 4 activities. ICSU is a great organization, but it does tend to think up really bad acronyms. So you'll see some really bad acronyms here. I'm talking about the panel area assessment on scientific information and data. I was a member of that. And then I was asked to chair the Strategic Committee on Information and Data, which spun off the World Data System, which I'll particularly talk about today. And then the final one, which is the final section of my talk, is a Strategic Coordinating Committee for Information and Data, which I also chaired. We couldn't think up any better names. But before I do that, I just want to run over some aspects of the big data challenge. And I've picked out 4 of them. The first one is astronomy that we've already heard about. And we are here, our solar system here, as far as our galaxy is concerned. And of course, astronomy has been an area of big data for a very long time. And the square kilometre array, which has already been mentioned, it looks likely that's going to go to South Africa. It hasn't been finally decided yet. But when it is built, it'll create an array of dishes, which is the equivalent of a square kilometre. When it's up and running by 2024, it will produce more data than all the computers predicted to be in the world by then will be able to process. Now, of course, one answer to that particular point is that, of course, technology changes quite rapidly. But it'll produce an exabyte of data per day, which is more than the current internet traffic. So the volume is just absolutely phenomenal of the data deluge, just from the square kilometre array. In CERN, with the particle physics, there's these enormous activities, 150 million sensors, 40 million times per second for the interactions, and 22 petabytes of data in 2012. I used to have a really good handle on exabytes and petabytes and so forth, but the numbers have just got so big now that I just haven't got the handle on it exactly. There's also the element of data distribution. So from CERN here, most of the traffic is going across to the United States and then in the direction of Japan, Far East, and Australia. But you can see a tiny link to South America and nothing over here, which I'll refer to a little bit later on. So astronomy, particle physics. In biomedicine, as a third example, the Human Genome Project springs to mind, where the Human Genome Project was intended to determine the sequences of the 3 billion chemical base pairs that make up human DNA, and identify all the approximately 20 to 25,000 genes in human DNA. A specific example within the biomedicine framework is the UK Biobank, which has worked with and continues to work with 500,000 people aged 40 to 69 to take measurements of blood, urine and saliva and track those over time. Enormous amounts of information from individuals concerning biomedicine. And my fourth one is in Earth observation. I showed you our solar system where we were before, and this is the same kind of thing except a slightly higher resolution, and that's where we are now. That's the hotel realm. This is the centre of Canberra with the Parliament building here. It's a wonderful shape. And this is from a high-resolution satellite image with pixel size of 0.5 meters. What I've done is to take a little extract from this area here and blow it up over here. So these are 4 people in their shadows and 3 people in their shadows from space, from satellite imagery. The satellite's about 700 kilometers high. And you can see the rest of it here. The date is important, not so much the actual date, but the fact is that wasn't a one-off. Those data are being collected a lot of times around the world, and from most of the major populated parts of the world, and will continue to be collected as well. So there's a huge data deluge in terms of Earth observation at the high resolution, at this sort of mapping scale, but also at the low resolution. So every half an hour, a satellite image like this is created. This is one from the Japanese satellite MTSat, and then there are 5 other similar satellites placed around the world. So the world is monitored by geostationary weather satellites, and usually when you see the weather forecast and see the clouds moving, they're from satellite data such as this. And there are many others in between as well. So there's no question, since the Second World War, we've shifted enormously in terms of our ability to do all sorts of monitoring, and therefore the data deluge. Last year there was a paper in Science by Hilbert and Lopez, which tried to estimate the world's total capacity for communication and storage of data. It's a rather dry paper, but it did have one interesting thing, and it said if you take all the world's data and put them onto CD-ROMs, and then just stack the CD-ROMs, just one CD-ROM after another, and stack them upwards, the stack would go from the Earth to the Moon and a quarter of the way back again, which I think indicates some element of this volume of information. Now, it's therefore, there's no question that we've got a big data challenge just as far as the big data is concerned, and a study by a company in the United States called IDC estimated that we'd have 35 zettabytes of data. In fact, I think zettabytes has 2 T's, but as I said before, I can write these things down, but I don't capture them so much anymore. 1 zettabyte is 10 to the 21 bytes. So we know that, but as we've heard in the previous talks this morning, there are, in some senses, more important questions of data complexity. So from cell to organism, from involvement of social science data with biomedical data, social science data with environmental data. There's also changing expectations on scientists. And I think a very good example of that, and I think it's a dreadful example, is that a man called Phil Jones, you may have heard of, about 2 years ago. He was the head of the Climate Research Unit at the University of East Anglia. And that created what Nature called the Climate Gate. And that was a scandal basically worked up by the newspapers based upon emails within the Climate Research Unit about veracity of climate change. Is climate change happening or not? And Phil Jones got death threats. He got lots of death threats in the post and emails and so forth. So to get to the expectation where a scientist trying to carry out science is threatened with death because he may or may not have suggested something about climate data shows an example, a morbid example, of the changing expectations. And finally on this slide, something we haven't really heard about so far, but there is a digital divide. The World Summit on the Information Society, about the 2 phases about 10 years ago, particularly commented on that. And I'll come back to that digital divide a little bit later. So there's a context. What I want to do now is to go back to the ICSU activities. So the first one is the panel area assessment on information and data. And saying this quite quickly, what we emphasized here is professional data management in science, to try to encourage and enable professional data management in science, to ensure universal and equitable access to data and information. But also not to forget about the question of who pays, because this stuff is not free of charge. Then ICSU had the Strategic Committee on Information and Data, and it was tasked to look, first of all, at the World Data Centers and the FAGs. That's the Federation of Astronomical and Geophysical Data Services. And many of these World Data Centers were set up in 1957 in the International Geophysical Year. And some of them have been successful, but some of them have become rather moribund. So we were asked to have a look at those. And we concluded that we should set up a new world data system, which I'll talk about in a moment, We also recommended that there should be a more prominent co-data, that's the ICSU Committee on Data and Information, which specifically looks at data information. And then we also recommended the ICSU national members and the unions are more prominent in professional and data information management. And it might come as a surprise to you that they're not very. So the various international institutes, international unions for different aspects of science, and the national members are not especially active in defining professional data and information management approaches. And I've got a recommendation on that in a minute. So let me turn now to the World Data System, and I'll spend most of the talk now talking about the World Data System and the next committee, the Strategic Coordinating Committee on Information and Data. Sorry, this slide is all words. This tends to be death by PowerPoint if it's all words. But the objectives are important. First of all, to enable universal and equitable access to quality-assured scientific data, data services, products, and information. Secondly, to ensure long-term data stewardship. My perspective on this is a century perspective, not least because if we think of the Intergovernmental Panel on Climate Change, then their predictions are the climate change by the year 2100, in other words, at the end of this century. That doesn't mean to say all of these data centers have to be keeping data for a century, but nonetheless, I think the perspective of coming into this question is not just a few years, it's a century. Thirdly, to foster compliance to agreed-upon data standards and conventions. And fourthly, to provide mechanisms to facilitate and improve access to data and data products. And we saw a little bit of that in the first presentation, that access to data there's no question that's still a problem. The status of the World Data System at the moment is it has a constitution, it has a data policy, it has an initial system architecture. But I picked out the two things in blue here, is it has a formal membership criteria and assessment process. And there's about 25 questions in this process of accrediting members. And the 25 questions are how an organization, which is the data center, is set up, how it's managed, what happens to the data when they come in, how they can be checked for the quality of the data, what happens if the power goes down, what happens if the funding organization stops, what about the long-term sustainability of the data. So this is getting back to the basic objectives of what we're looking for. And then the second thing in blue is that as a result of an international competition run by ICSU, an international program office has been set up in Tokyo, and it had its inaugural event ceremony last week. So this provides a focus of attention in Japan, but for the worldwide activity of the World Data System. Finally, on these slides, there was a first World Data System conference in Kyoto last year, and there'll be World Data System activity in the Co-Data conference in Taiwan at the end of October. So far, there have been over 140 expressions of interest in participating in this, 58 formal applications for membership, and 35 regular members approved. Other characteristics of members as well. I anticipate we'll get to a position of around about 100 formally approved members to produce quality-assured data within a year or so. It just takes a little bit of time to get all the applications finalized and the whole evaluation process done. And I think there's the chance for this very practical approach to be fundamental as a science. Examples of these, and some of you will know some of these things already. There's the Antarctic Data Center at Hobart in Tasmania. There's the Climate Data Center in Hamburg, Oceanography in Washington, D.C., in Beijing, Renewable Resources and Environment, Solid Earth Physics in Moscow, but then also services of information, things like the International Laser Ranging Service, the International VLBI Service for Geodesy and Astrometry. And so this is the idea of providing both data sets as chunks of data, but also services. If I could just make a point about that in relation to science data, is that what seems to have gone missing to a certain extent is the experience of the operational data supplies in science. And I'm thinking particularly of meteorology, where meteorology for decades now has had operational transfer of information. Of course, meteorological data has been used for scientific investigation, of course, and meteorology is a science-based discipline. But those centres haven't really so much been used, those facilities of operational data supply and experience on that hasn't so much been used, perhaps as it could be. So the final chunk of the talk is then looking at the Strategic Coordinating Committee on Information and Data. And we produced 14 recommendations. This report and all the reports are available if you'd like to look at them on the ICSU website. I've picked out from the 14 6, which I think are particularly relevant to the meeting. The first one is communication of best practice on data management, because many scientists, many projects, and indeed the national and union members of ICSU say, well, how do we do this thing called data management in science? What is it? For those who know and those who are in the know, then it's all fine. But for those who are on the outside, it's not so fine. So what we did is produce a deliberately brief document on best practice in data management. And it's got 3 parts to it. And the first part is what topics go in, and it's things like policy, governance, standards, access, archiving. The second part is a set of active verbs, so what you should actually do. I would be critical to a certain extent of a number of reports which have been produced in the last few years about this area of research data management. The European Commission riding the wave, the Alliance of German Scientific Organizations in 2008 on science data management, and there's a new one going to come out from the Royal Society. These are all good documents. They tend not to say what people should actually do. They say research data management is a really good thing and organizations should do it, but they don't go the next step, which I think is needed to go the next step. So we've done this document with, as I say, the first point is what are the topics, the second point is the active verbs, and the third one is examples. So examples pointing, they're all on the web, to the Protein Data Bank and how they do research data management, Intergovernmental Panel on Climate Change, how that does it, Global Earth Observing System of Systems, and so forth. So that when people come to do the data management step in this big activity, then they're not starting from scratch. The second recommendation is to explore and agree that terms used in open access. And I think we're in a bit of a difficulty here because the word open is a terribly friendly word, very positive. But what have we got? We've got open access, open data, open archives, open content, open knowledge, open notebook science, open publications, open access publications. And much as those people who are keen on open access, and I've talked to a lot of them, they do acknowledge that the terminology has now become rather confusing. The specific example is open access data has different meaning to open access publications and different implications, including on the who pays. So I think, and we thought it needs to be rather tidied up. So we haven't come up with a proposal of what it should be, but suggesting there should be a forum. And this is where, back to the acronyms, so, ICSD and INASP are parts of the ICSU family concerned with publications, and CoData is concerned with data. The third one I want to pick out is improve the process of creating data as a publication. So this has been quite a big thread in the last few years, particularly interesting, of course, in this meeting and to Elsevier. A number of publishers have been inviting the data to be included in the publication or linked to, as it were. The reference was made earlier on to Pangaea. And that Pangaea project is part of one of the World Data Systems Centers. And it's partly about the behavior modification in scientists. That is, increasing the recognition for the production of high-quality data, as well as high-quality publications. And it's still quite a battle to get scientists to do that with their own data, or indeed with processing of other people's data. In the course of the SCID committee, we also had a look at the potential role for legal deposit libraries, which go back to the King of England in the 17th century, who set up the first legal deposit library because he wanted to have a copy of every book that was published in England at the time, and that's the start of what became the legal deposit libraries. Most countries, I think all countries in the world, with the exception of the failed states, have got a legal deposit library system. The Netherlands is the world leader at this process. If data were able to become a publication, then could they become involved in the legal deposit library approach? If that were the case, they'd be more likely that the long-term, century-long timescale for safeguarding data would be recognized. We recommended something which is just practical, of using the CODATA and the World Data System conferences more actively. They alternate every couple of years. We recommended practical help to the less economically developed countries. I think the message here is that although IT infrastructure, the network and the computers and so forth are expensive, they're not as expensive as developing a Large Hadron Collider or doing major physical science infrastructures. So it's information and data in science is rich in opportunity for less economically developed countries, but relatively low cost. I'm not saying it's necessarily zero or low cost, but relatively low cost. And what we did in the report is to suggest how different parts of the ICSU family can participate actively in these things. So we're not just doing the arm waving of saying let's help less economically developed countries. But one way of doing this is to try to seek World Data System nodes, new data centers in less economically developed countries. So far the only one is in South Africa. So why shouldn't there be more in Africa, for example, these centers, particularly if you accept my argument that the cost is not so enormous compared to other science activities. And as we've heard already this morning, there is linkages to the cultural, economic, and social evolution of countries as well. And then one important idea is partnership and mentoring between the existing parts of ICSU and activities in less economically developed countries, including the national and the union members of ICSU. So to try to do something more practical. And the final point is cooperation with commercial companies. Many scientists around the world, many science organizations are fearful of commercial companies. I don't know why, because the taxes pay their salaries. And we felt there would be mutual benefit. For example, in the case of ICSTI, which is a science and technology organization linked to publishing, they worked extensively with Microsoft. As an illustration here. And this could be developed further for mutual benefit. My final slide, Chairman, is this question of fourth paradigm, which was referred to a little bit earlier. And this can be set in the context of the history of sciences. The first paradigm was essentially observation, description, and experimentation, for example, Ptolemy or the Arab scientist Ibn Battuta. And from all these observations and mapping, we moved on to the second paradigm of theoretical science, for example, Newton. The third paradigm, maybe is in the last 50 years, is simulation and modeling. Climate models are the big one that we know about. And now we're said to be possibly in the fourth paradigm, which is characterized by data-intensive science. So not just that we're in big data, but it's data-intensive on the science. For example, the International Virtual Observatory Alliance, the IVOA. You could say that the fourth paradigm is actually like the first paradigm. So I'm not necessarily wedded to this. But what I would say, what I think is important, is that if the fourth paradigm of data-intensive science exists, then we're at a very, very early stage of it. And as we're at a very early stage of it, we can influence its growth and development. We're at a position where we can help it develop in a number of ways. And to a certain extent, one can see this conference as being a way of trying to shape what that fourth paradigm is. So what I've given, Chairman, is a summary of the work of the International Council for Science in trying to assist in the shaping of what happens, but in a very practical sense. Thank you very much.